Yes, recording has been
Uh,
started.
Good day, everybody, and Merry Christmas to everyone. Today, today's lecture will be given by Pratik Ghosal. He has done his PhD from Bose Institute with Shamsubroda, and now he's postdoc at SN Bose National Center for Basic Science, Kolkata. And today he will talk about quantum channels and the capacity of those channel, classical and quantum capacity. Uh, and if someone asks any question, please unmute yourself and can ask the question directly. And I hope Pratik will be okay with that.
Yeah.
And Pratik, you please start and just remember you can go slowly because if you want, you can continue next week also.
Okay.
So, okay, start Pratik, please.
Thank you, Shorolvita, for the introduction. So today I will be discussing this correction of quantum channels while the receiver is accessible to making measurement in the environment. So I'll discuss this topic at the level of a beginner also, so that many of the audience who are beginner stage, they can also follow, I think. And one more thing I want to mention that if you have any problem regarding understanding my handwriting, please ask me, I will clarify. So when we start reading quantum mechanics, the postulates tells that for evolution in part, if you have a closed quantum system, so if you have closed quantum system, then the evolution that you are allowed is unitary evolution. Meaning, if I have a system which is prepared in some state rho, then the evolution is given by some unitary u rho u dagger, where um, u dagger equals u dagger u equals identity. And the
Pratik,
significance, yes,
for closed quantum system, the in general the evolution can be non-unitary also, right? It's
yes,
like okay.
yeah,
For
I'm going.
now, you are just considering the unitary.
Yes, for closed quantum system, we can. Oh, you are saying that even for closed quantum system, the unit evolution can be non-unitary. That you are asking?
Yes, yes, yes.
Okay, so I thought that for closed quantum system, the evolution is always bound by unitary evolution, and for open quantum system, when the system is interacting with some other environment, then this non-unitary evolution comes.
Okay,
That was my impression.
okay.
And so the property of this evolution is that it is reversible. Means it is reversible means if you know that rho has gone to sigma, then there exists another unitary which is u dagger that will take sigma to rho. Now, if we consider open quantum system, then the most general evolutionary dynamics is mathematically represented by linear CPTP maps. So
You are writing something, but I can't see. Everyone
oh
sees, I can see something.
no, I think I'm on.
I think none of us can see.
Oh, okay.
Hey, Shomrat, can you also? Shomrat has taken his phone, which is connected with the Wi-Fi. What's the problem? Well, Shomrat has taken the phone, and it was connected to Shomrat's phone. Wi-Fi connected to. Yeah, I think now it is visible,
Yeah, now
right?
it came back. Okay.
Yeah. So linear CPTP maps, or sometimes we call it quantum channels, where the state evolution is described by some lambda rho, where lambda is a linear map acting on the lambda is a linear map acting on the input Hilbert space to output Hilbert space. And this is trace preserving, so that means trace of lambda rho equals trace of rho. And it is positive, completely positive. Completely positive means, first of all, it is positive, meaning, so for all operator O, which belongs to the positive a positive, which for all operators which are positive, lambda O is also belongs to positive. And furthermore, if you take an extension of this map with an arbitrary ancillary system, where this identity can be on any arbitrary dimensional system, then O ancillary and the system is also belongs to the positive of HA tensor HB. So that is meant by completely positive. Now the property of this evolution is that this evolution is irreversible. So irreversible means that not all information, not the complete information is retained by the system. And some information is actually leaked to the environment. So a simple example to show this is consider the completely dephasing channel. So if I take completely dephasing evolution, so then my initial, so I'm considering cubic channel. So if I take the input block sphere like this, then if I act the completely dephasing channel, then the what is it, image of the channel is like just these two poles, the 0 and 1. So if you take a state from these, or if you can take a state from these, both of them gets mapped to a same point. And given the output of the channel, which is this, you cannot recover what was the initial state that you have sent, whether it was this or this. So we get to see that under this completely dephasing channel, or in more general any other quantum channel, this information is not completely retained by the system, and some of the information is, or all of the information is actually lost to the environment. So to describe this information being lost to the environment, we have a suitable description for defining these quantum channels, which are otherwise linear CPTP maps. And that description is nothing but the Stein-Springs dilation. So what is Stein-Spring dilation? Stein-Spring dilation says that let's take you have been given a channel lambda, and you are giving some state rho, and as an output of the channel action, you get some lambda rho. Now these I can think or model like that. So we have a system which is rho, and we think that there is another environment. So this is the system and this is the environment, which is this part is the environment part. And you consider a system and environment to be coupled, and you can take an arbitrary fixed state for the environment part, and on the system part you take the two system as a whole, and on this system you apply a group, and this combined system plus environment, the composite system, evolve under a unitary evolution. And after the unitary evolution, you have some system, some evolved state for the system, and some evolved state of the system environment joint state, and you trace out the environment part. And what you are left with is the evolved state of the system, which is nothing but lambda rho again. So mathematically, this lambda rho I can recover by taking the system and the environment joint state, and since they form a closed system now, they evolve under unitary evolution like this. And then after the unitary evolution of the system environment joint system, I will trace out the environment part to get the system output state. So this is called the time spring dilation. So it actually gives us a model of how the open system, to describe the open system dynamics of the system as a closed system evolution of the system environment as a whole composite system. Now this I can also represent with another equivalent description, where I don't have to take a, so this is just mathematical another way of representing this. So I will take the input system as a row S, and I will apply, or we can apply a isometry operation on the system to get actually the system as well as the environment composite system. So this is some composite system environment, and I will trace out this part of the environment again and to get back the system default state. So lambda rho S can also be represented by trace over environment of V rho V dagger. Now the important thing is that while U was a unitary operator, so U was any unitary, and this unitary was acting on this, it's a linear operator on HS and HE. So V is an isometry operation. So V takes the HS, so it's a map from HS to, sorry, so V belongs to, so it involves the system Hilbert space to system environment Hilbert space. And by then taking out the trace, I will get the system state. Now, so what, due to, since we are not able to access the environment part, so we get only this information that is being carried by the system part only. So that's why some information is being lost to the environment, or some information is locked in the correlation between the system and the environment after the unitary action. So there is another.
I have just a naive question, that you are saying that information will be lost in the environment. Can it be possible that the information, maybe some other information, can come from the environment?
From the environment. So
yes, maybe environment is an information hub, and when you are going through this channel, some information can come from the environment. That can be possible.
Yeah, I mean, when you are tracking when you are tracing out the environment, means you are not accessing the environment. So basically, the information is actually stored in the system part, environment part, and the correlation part. Now you are not looking into the environment part. So you are only accessing the information that is in the system part only. And since this V isometry, so this V isometry, since it is preserving the information, so whatever information that you have put in the input, that is being preserved, and this information is in the correlation in the system part, environment part, and the correlation. And just because you are not seeing the environment part, you are not getting the complete information. That's why I'm saying this information is hidden from us, and it is actually stored in the environment and the correlation.
Oh, okay.
But I think what you are trying to say,
I think Saurabh is asking that whether the environmental state omega E can supply some information. So to answer this question, Saurabh, the point is, when you give this time spring model, we don't change this omega E. For every all possible row S, this U is fixed, this row S is fixed. This U is fixed, and omega is also fixed.
yes.
So that's why your environment does not give you any informations from that perspective.
I mean, environment can't transfer information from WE to lambda.
Just a simple comment. I think if you can consider that U as a swap operator, then actually the environment state come to the system part, right?
Yes.
So whatever environment you put, there is possible that the information is actually coming to the directly to the system part. You just make a swap between the system and environment.
Yes, but since omega e is taken to be constant for any state row,
And
it
when
actually trivial information.
when you give a model for when I give a model for the Steinspring model for a channel lambda, then immediately this omega e would be fixed once you fix the u.
No. That is up to unitary, I think.
Will it be up to unitary?
Yeah, because the total unitary and the environment on all of them, I have the unitary freedom to give the Steinspring. Means I am saying that in principle, it is possible that actually the environment state, I don't know whether it is actually some information or not, it actually comes to the system part after the evaluation. It is actually possible if you consider U just as a swap operation.
Mhm.
So the system state
Yeah.
becomes the environment state.
Mhm.
I'm
I
saying
mean-
in that sense, yeah, obviously it can be a question that whether it is a true information, something new information is actually coming. That I am not saying, but it is in principle possible that the environment state is actually coming to the system part
Yes.
for some unitary dynamics.
Yes, yes, because since we are considering only this omega e to be fixed for all state, then it carries no information. That's why we can make the comment that it is not coming.
Yeah,
But
yeah,
if you-
I understand.
I mean,
And
in
he also
principle,
was,
ha-
well,
in
maybe it
principle,
was still, but finally this environment is actually fixed, at least up to unitary also. But in that sense, maybe no information is coming. But as Shouru was saying, that whether it is possible that the state of environment is actually coming to the system, but this is actually obviously possible by choosing some unitary which is just as a swap operator.
Yes, because actually I asked that because usually in the self-testing thing, people usually does that. You have a row state and then you have ancillary, which acts like environment, and you do the swap operation. So the property of the unknown state comes into the environment. I mean the ancillary, where people measure and decode the property of the state. So this is something like that kind of similar.
I would like to add one point over here that if you want to know that how information is manipulated, one way to see is that if you now trace it over the output system and you consider the complementary channel, then you will get some idea about information transmission. But that is not exactly what information you are getting, but that is a channel where what you are doing is in this Steinspring model, you are tracing out not over the environment, but over the output Hilbert space. So what will happen is that you will get a mapping from the input state to the environment. So that means you are considering the complementary channel. That is actually known as the complementary channel. So from that, by looking and analyzing the properties of the complementary channel, you might get some idea about some information which is getting leaked into the environment.
yes, exactly. So means this, if you calculate if you take only the classical information only, then you can calculate the mutual information between this lambda c row and row, then you will get the information that is being deposited in the environment.
Okay. Okay, please continue.
Okay. So apart from the Steinspring, representation, there is also another well-known representation, which is this Krauss representation. So now Krauss representation we can derive from the Steinspring representation, just like this. So from now on, I will take only this isometry picture, which is convenient for our purpose. We can also take the unitary picture, but I'll take the isometry picture. So in the isometry picture, what we have some system state row entering and some evolved state of the system environment, and we are tracing it out, and we are getting the effective channel action as the system. So instead of tracing it out, we can think like this, that there is an agent who is accessing this environment part, and there is another agent who is accessing the system part. So for the clarity, I will call this input part sender and the output part of the channel as receiver. and the environment part as E. So the receiver, the environment agent is actually implementing some POVM. Let's say he is implementing some POVM on his part of the system. So and after doing so, depending on the POVM element that he is doing, let's say on one round he has got, so environment is doing this particular POVM operation xk, and on one round he has got the kth outcome key. So then the system, or then the state of the system will be steered like this. So we have this feed dagger, and you are doing this xk acting on environment and identity acting on the receiver end. And when you trace out the environment part, you actually get the post measurement state of the system of the receiver like this. And let's define this state to be denoted by some AK row AK dagger, where AK are operators. So these belongs to linear operators from H input to H output. So these are linear operators taking input Hilbert space to output Hilbert space, and that is the definition of that is the defining property of these operators in this equation. Now, since environment is not communicating his outcome k, so on average, the state of the receiver end will be nothing but the summation of the k. So if you take summation, so if no communication is there from the environment part to the receiver part, then the output state will be nothing but pk rho k tilde. Yes, Manasi, you have a question? Hello?
Hey, she has mistakenly raised her hand.
Oh,
yeah, maybe. You.
Okay. So the effective state of the receiver end will be the summation of the k, and if you take summation over this actual thing, it will be dagger. And since trace is a linear operator, you can absorb the summation sign inside, and summation over you can do like this. And this is nothing but identity again. So you are basically left with the channel state. Action of the channel state. So that we can write like this. So this representation is called the Krauss representation of the channel. And these operators, set of operators AK, are called Krauss operators. And if you take trace, so we have taken lambda to be a trace preserving operator, and if you take trace, you want this to be the trace of the initial system, and this actually implies that you will have this property. Now this representation of Krauss decomposition, it is not unique, and this is, you can see that this actually this description of AK actually comes from considering the environment doing this POVM measurement and not recording or communicating his outcome to environment. Instead of, let's say, taking this XK POVM, this environment could have taken pi K POVM, which is a different POVM. And then the resultant state for each outcome at the receiver end would have been steered differently. But again, since no communication is there, on an average, the state is same for both the measurements. So this actually this actually points to the fact that this Krauss representation is not unique. You can have multiple different representation of this channel action in terms of Krauss operators. So Krauss representation is not unique, and it depends on the POVM that was being chosen by the environment part. So, I mean, for more clarity, I can write the same channel action like this also with the different sets of Krauss operators. So now we define A to be the set of all possible Krauss representation that are compatible for a given channel lambda. Okay. So till now, what we have discussed is basic things that we all get to know from standard books like Nielsen and Chuang, Skill otherwise. But now let's try to understand what is this new thing, which is correcting the information. So as I said, that output of the channel, it doesn't capture the whole information of the system. But now consider this picture that, okay, there is this input state row and we are getting some output, and the environment is doing this measurement in different possible bases, and this environment is transmitting the outcome, classical outcome of his measurement, let's say K, to the receiver end. And the receiver, upon receiving which particular measurement outcome has been obtained, the receiver can apply a subsequent correction channel that I call pi phi k. So it's like this. So let's say the environment this agent has made this xk POVM. Yeah, Nirmanda.
Yes, Pratik, I had one question that, as you said that the cross representation is not unique. So we can have different types of cross representation. So is it possible that we can have some sense of optimal cross representation with respect to some operational task or something like that?
Yeah, I will go there. I mean, I will not be able to fully answer your question, but in my later part of the talk, I will try to motivate what will be a suitable cross representation for calculating a particular quantity.
Okay, fine. Okay, thank you.
Okay, so just as I was saying, that environment is doing some xk POVM and he's communicating this classical outcome K to the receiver end, and the receiver, upon receiving the particular outcome of the measurement of the environment, is applying some correction channel phi K. So what is actually being done is this before this crowd. So as we look here, yeah, here. After the kth outcome, the effective state at the only for the kth outcome run, the effective state of the receiver end is given by this. And let's consider that the receiver, upon receiving the kth outcome, he applies this phi k map on the output state. So on that run, his effective state after this correction will be denoted by this. And after then, since we are considering all possible outcomes, we will sum it over again for all possible values of the measurement outcome K, and we effectively get a corrected channel for the row. So this actually takes into account the measuring the environment and correcting accordingly by the receiver end, and this actually produces this corrected channel lambda be corrected row. So this concept was first introduced by Gregoretti and Warner in this paper. The name of the paper is also very nice, Quantum Lost and Found. And so in this reference, you will find this idea being described. So this is a corrected channel. So intuitive picture is like that. So environment is being measured, environment is accessible, and one-way classical communication. So this is classical communication, one-way classical communication from the environment to the receiving end being made, and the receiver doing this correction operator, correction channel 5K. Now after that, Hayden and Keene.
Pratik, I have a question.
Yeah.
Like, shouldn't be this corrected channel be close to identity or something? Like, we are correcting the channel, that means we should retain the state. Okay.
No, it depends. So how much amount of information that you will be able to recover by proceeding this protocol, it depends on the channel, particular channel that is being considered. So it might be the case that by only one-way classical communication, you will not be able to obtain the whole information. So maybe receiver have to again communicate to environment another way, and then back and forth. So unbounded both round classical communication is even then, even both round classical communication being is also allowed, then also it might be the case that complete information is not being retrieved. So what question you were asking, that if by implementing this correction protocol, will I be able to make the channel identity or noiseless completely? Well, for certain class of channels, this is the case, and I think I will discuss this in my second part of the talk, where the main thing is that if you take these channels to be of certain types called the mixed unitary, means if this channel can be represented as a convex mixture of unitary channels, then and then only you can recover the full information, and otherwise it is not possible. So I will.
Okay, but okay. Okay.
Yeah, you have other questions?
No, I was just adding the point that maybe we will not be able to recover whole information, but our goal should be that it should be close to identity or something like this.
Yeah. So, I mean, as I said, certain class of channels are only suitable for making the perfect correction. Okay. So then, Hayden and Keene, so they have a paper in 2005 where they defined one particular quantity of interest. So in this reference, they have looked into one particular property of this corrected channel. And the property that they are interested in this is the single shot classical capacity of the corrected channel. So for the beginners, I would like to first describe what is meant by classical capacity or any kind of capacity of a quantum channel. So let's consider the single shot capacity, classical capacity. Single shot classical capacity of any channel. So let's consider you have a channel lambda and you want to convey some some classical information. Let's say you have an input index x, input index, that is, let's say, a beat. Now this beat information you want to communicate through this quantum channel. So what is the procedure? So first of all, you first need to encode this classical bit into a quantum state. So depending on what a particular x you have received, you will first encode it into suitable state. So first, for x equals 0, you will create rho 0 state, or for x equals 1, you will create rho 1 state. So that is for the encoding part. And now you send this rho x state through the channel, and after the channel action, you obtain some sigma y, let's say. So sigma y is nothing but lambda acting on rho. So for rho x, you get some sigma x, let's say, for same index. I mean, why I was using this different notation, notation for this output symbol is like, so for 1x, you can have multiple input. So in general, you can have the input index and the output index different. So you can have more than 2 index also. But for the time being, let's consider the simple case where y and x are of same. So you get sigma x depending on lambda rho x. Now on this lambda sigma x carries actually the information of the system. Now you, on the sigma x, you do some kind of measurement, and that measurement, so you feed the sigma into this measurement setting, and you get 2 outcomes. I mean, either x equals 0 or x equals 1, or let's represent it as y equals 0 and y equals 1. So in this way, from classical, you have classical data, you encode it into a quantum state, and you send the quantum state through the channel. You get an output quantum state, and from the output quantum state, you are decoding the message by measuring it in a measurement device, and you are obtaining some classical outcome. So depending on the outcome, you will have some kind of mutual information, which is the output variable and between the input variable. And this mutual information is actually dependent on the particular details of the what went inside. So first, it will depend on the encoding. How did you encode the classical channel? So whether you have taken appropriate encoding states. So this rho 1 and rho 2 may not be a good candidate for encoding purpose. And also it will depend on the measurement that you have done. Maybe you have encoded it rightly, but while decoding, you have chosen a bad measurement, so it is not giving you correct things. So for that, you have to optimize over all possible encoding and decoding, and then you maximize this mutual information quantity, and then what you get is this channel capacity single shot of the channel lambda. So this is how single shot channel capacity or single shot classical capacity of a channel is being defined. Now, similarly, here we are interested in finding out what should be the single shot capacity of the corrected channel. So here, corrected capacity of lambda is actually defined by the channel capacity of lambda. Corrected. And now, if you remember how lambda correlated corrected channel was defined by these, here whatever you have done is that, okay, you have, based on the output k, you have applied some recovery channel. But now, as Nirmanda was asking this question, that whether among the set of all possible Krauss representation, is there any choice of a particular Krauss which will give you some optimal advantage? And if you see that while making this correction, the measurement of the air environment was playing a key role. So you have to optimize over all possible POVM that was being implemented by the environment. And this actually steers the state in the receiver end. So you have to take into account the optimization over all possible POVM operation. So you have to, only for a given channel, you have to first optimize all possible Krauss representation, because as I said, that Krauss representation is actually related by the measurement choice of the environment. So you have to supremum over this Krauss representation that belongs to A lambda. So A lambda, as I have defined earlier, A lambda is the set of all possible Krauss operators that are admissible for a given channel. And also, after that also you have to choose suitably what are the set of correction channels you have been used. So then also you have to take in another optimization or supremum that you have to optimize over all possible correction operations. So given these two conditions, you want to find this supremum of this Shannon capacity of the lambda corrected channel, and that you define as the single shot corrected capacity of the quantum channel. So Nirmanda,
Hello.
Nirmanda.
So why are you calling it single shot?
Single shot means I am using only the channel only once, and I am defining its capacity only from the single use of the channel. Because in quantum channels, it is the case that if you use a channel in multiple times, if let's say you use the channel once, you have used the channel and n times, and you can input n different encoding in n different input state, and you get n different output state, and then you can do a global measurement on these different n state, and then you can regularize the capacity by taking that, okay, what is the information that I'm getting, and divide it by taking an average per use of the channel. Means you can think like that. So you take classical capacity like C of lambda, and you use it n times. Means you have the channel in parallel, and then you feed like rho 1 dot 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 rho n, and you get sigma 1 dot 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 sigma n. And for this, all these channel, you can do a joint measurement on this and get a classical output y, y. And this x input you can input into n different state. So you can have this, what is called this n parallel use of channel, and you take the classical, calculate the classical capacity, and you average it out with the use of the channel. And then if you take the limit of this n to b tends to infinity, that is actually defined as the classical capacity of the channel. That is the regularized version. But we are not looking into that. We are considering only the case where the channel, only one copy of the channel is only available to me, and I am using it to get the best out of it. That's why I'm calling it a single shot channel.
But for measuring the mutual information, you have to consider an ensemble of states that are being sent through an ensemble of channels. That's
Yes,
how you calculate probabilities.
correct. But then also we are taking that, okay, at one run, I am taking only one copy of the channel. I am not using multiple copy of the channel in parallel and sending the state. I mean, I can use one channel in one, okay, if x is 0, then I will encode this in rho 0 state and use one channel. And x equals 1, I will use rho 1 and use the same channel in different, for different input. But I am using only one channel. But when you are defining this regularized version of this regularized version of the channel capacity, then you actually consider that you have actually n copies of the channel in parallel, and you are encoding the input state, input symbol into n into this rho 1 tensor, rho 2 tensor, dot 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 dot, dot rho n. So you're using n partite state for encoding purpose, and then you are sending each of these state through each of the channel. N channels you are feeding with this n inputs, and you are getting n outputs, and then you make measurement on the whole system. and then you calculate the what is the mutual information, and then you regularize it in this way. So then I'm saying in that case you are using n channels, physical channels, n channels in parallel. But in our case we are using only one channel and one copy of it. We are not bringing in other copies of it. That's why it is called single shot.
Yeah, thanks. I cannot see your video, like your slides. Can you, everyone can see it?
Yes, we can see his slide.
Oh, yeah.
Pratik, I just have the similar kind of question what Arun asked you that
Yes,
to
yes.
calculate the mutual information, you need probability distribution. Now, to generate probability distribution, you have to use the channel in certain number of times, right? Like let's say m times you need to use this. So that means let's say you are encoding x equal to 0 information into row 0 and you are sending to the channel lambda, but you have to perform this job at least m times so that you can have a valid probability distribution. And
Yeah,
from
but
there you can calculate mutual information and all that. But you are saying that,
yeah.
that the number of runs of the experiment is not important. That is your experiment one.
Yes,
And
yes.
and for n number of encoding, you have to perform n number of experiments, basically.
Yes, I
For
mean,
different input. That can be one strategy, and another strategy can be you take a n-partite state and you put into the n parallel channel, and then you will get together. Together you
yes,
will get everything, right?
I mean, even if you want to calculate this quantity, then also you have to repeat this experiment multiple
I
times.
understand.
So,
I understand. Number of runs is not important here.
yes, yes, yes.
So then I have two questions basically. That one is why you are saying it is classical. I mean, why the term classical is coming, where it is coming, the term classical, because you know what we understand as classical is very different what you are saying, right? And another question is when in this scenario, when you have a n-partite state, you can create an entangled state also, right? And you input
Yes,
this and your channel is like that and you will get some output. Now,
yes,
when you're measuring you can also measure in the entangled basis also instead of
yes,
separable basis, and you will get different outcome, like n number of outcome maybe you will get, right? And from there, you will coarse grain it into again two outcome scenario, just to calculate the mutual
mutual information.
information, right? Now,
Yes, yes.
the question is whether how you are cross graining in that scenario, whether it will impact the value of C or not.
Yes, so the last question is yes, obviously. I mean, while calculating this C, you have to take into account all possible decoding and encoding strategies, and then you have to optimize over it. So, as I mentioned here, so when you want to calculate the capacity, you have to maximize or optimize over all possible encoding and decoding strategies. So you have to take into account all possible strategies that you can come up with for encoding purpose as well
Okay.
as the
So you will just bypass this problem defining in this way that
yes.
it is already in that. Okay, and that classical one. Why? Because in many literature also I read that they are telling this kind of classical, and this word, the use of this word, I'm little bit confused about that.
Yeah, because actually when you are using the channel only to convey this classical so even when you are using this channel, you are basically using this channel to convey this classical information only, X, and you are getting the classical output Y. So you are not actually interested in looking into so a quantum channel can be used to send quantum systems. So in that case, if you are interested into looking into the output states quantum properties, like say coherence or some other quantum properties, or maybe some kind of entanglement sharing, then you are interested in the quantumness of the output and the input state. But now we are using the quantum channel, but to convey only classical information. So here this X and Y are the quantity of interest to you. And these are classical.
Okay,
So that's why
this classical is not what we understand as classical. That is some non-contextual on T. That is the definition of classical, right? But here the term classical is little bit different than what we usually.
Yes. It is just this classical variable you want to communicate. That's why it is called classical. And if you are interested into this quantumness of the input and the output state, then you have to consider the quantum capacities.
Yeah, okay.
Okay, I think Arun had raised a hand or something. No?
No, I have not raised my hand actually.
Okay. I just saw your name blinking. That's why. Okay. So, Nirmanda, you were asking this question about this finding the optimal Krauss representation. Was my answer?
Yes, it is clear. So you are actually doing two levels of maximization over here.
Yes.
Yes. So actually, Mani, maybe you may come up with this answer later on. That one very interesting thing whenever we study about capacities is whether the capacities are additive or not. So what can be said about like the additivity of this kind of capacity? Like it is a very difficult question to answer. I know that because additivity of classical, or in fact any quantum channel is a capacity is a very difficult thing to say. So this will be one of my questions. And another question that I have over here is that computationally, calculation of this kind of capacities should be very hard, isn't it?
Yes. That is very hard. Because this optimization for all possible Krauss states and correction channel.
So I want to make a comment on this point. So the point is, so there for this quantum channel and regarding the classical capacity, different scenario comes up. For example, what kind of encoding I am doing and what kind of decoding I am doing. One of the very easiest encoding and decoding could be product encoding and product decoding. Okay, in that way, people define this capacity like people define CPP. The next phase could be, okay, you define the encoding in a product way, but do the decoding, perform an entangled measurement, okay? So that is called CPE. And for the CPP and CPE, this normalized formula, this C lambda where limit n tends to infinity 1 by n, C lambda tends to n, that has been defined. For the product encoding and product decoding, that is just like a mutual information type of quantity, what Pratik defined earlier. And for the product encoding and entanglement decoding, Hollebo, Schumacher, Westmoreland in 1999, they give a formula which gives the upper bound of that quantum classical capacity that comes from the Hollebo bound. However, the most general scenario could be entangled encoding and entangled decoding. And there, whether that capacity for the same channel would be higher than the product encoding and entanglement decoding is unclear. And it is a very considered to be a very hard problem, and it is still unsolved. So that is the things here. And the single letter formula for entanglement encoding and entanglement decoding still not known for general channel. Although for some specific channel, the formula is known for entanglement encoding. I cannot give the reference immediately, but okay, I think this is known. But those kind of channel does not show super additivity. Super additivity means what you understood, that the things would be highest. But in general, this is an open question so far.
So for entangled encoding and entangled decoding, super additivity is not being manifested, that you were saying?
Yes. In case of a classical capacity, but in case of a quantum capacity, people have explored it.
Yes. Okay, so now I'm moving forward, and now I will discuss two important results. So first I will, so since this calculating this corrected capacity is in general very hard, let's try to understand, let's try to have a feel for it by looking into some examples. And these examples are the extreme examples. So,
Pratik, if your example is small and
you
can just wrap it up maybe within 5 minutes, and maybe you can continue the next week also.
Yeah, sure. I will just mention the two results very fast. So you consider this channel lambda rho, which is a measure and prepare channel. So, so in the picture like this, you have this channel and you are giving in some rho, and you are measuring it in a particular K basis. And depending on the outcome, you are preparing a state K sigma. So this is the outcome, what is the probability of getting K as outcome, and this is with that probability you are preparing a sigma K channel state, and this is what is called the prepared and measure and prepared channel. Now you can see that the corrected capacity of this channel is, I mean, if you take K to be between 0 to d minus 1, then and this row belongs to CD, then you can show that this channel capacity of the lambda corrected is actually logged in. So you get full information of what was being said. So with environment assisted, you are getting the full information of what classical index was being encoded into this row state. And for getting this correction lambda corrected channel, the optimal choice of recovery map or the correction map is for all sigma you take the pin map. Like for all state you prepare this K state. So after all, the lambda K row, lambda corrected, will look like this. So you actually have all the K symbols. So for this, you have the full classical information retrieval is possible. So this was one particular example, and another example that is very much important is that they have a theorem in that Hayden and Kim paper. It is saying that for any qubit channel, C corrected of lambda is log 2. Means however bad your channel is, if you have access to the environment, you can have full classical capacity. And this proof is very simple. So I'll just so okay, you want to send for so you have a lambda which acts on C2 systems, and it takes to C2 only. So for C2, you can, how many classical variables can you encode in a C2 system? And that is 2. So for x equals 0, you will have psi 0. And for x equals 1, you will encode it in the psi 1 state. And this psi 1 and psi 0 need to be orthogonal. Means otherwise you cannot retrieve the channel. You cannot retrieve the information from the encoding itself. So let alone forget the passing through the channel. If you encode the x0 and x1 into two non-orthogonal states, then after encoding you cannot retrieve the information. So it has to be orthogonal encoding. And then what you do is that you send this psi 0 or psi 1. So psi I you send it through this environment channel, through this channel. And after the isometric time string picture, you will end up with some state phi I, and phi I is now a receiver environment joint state. Now, depending on the input I, you will either have phi 0 or phi 1. And so basically you now have two orthogonal states shared between receiver and environment. And there is a famous result by Walgett and Hardy. So I forgot the reference, but I think this is very much well known to the community. So I am just calling it Hardy-Walgett result. I forgot the reference to any. So what is Hardy-Walgett result is saying that if you are given two orthogonal multipartite state, you can always distinguish with by LOCC. And even more powerful thing is that if this state is bipartite state,
This it should be multipartite pure state, right?
Yes, sorry, I should have mentioned multipartite pure state. And if this is a bipartite pure state, then this discrimination, local discrimination task can be done by only one-way LOCC. Meaning, so let's consider this receiver and environment, and they are shared this phi 0 or 1, let's say phi I. And what the standard protocol to discriminate whether it is phi 0 or phi 1 is that environment will choose a suitable basis measurement, and the outcome he will convey to both receiver, and receiver will depending on upon receiving the outcome, he will do certain measurement which will always reveal whether I is 0 or 1. So by one-way LOCC, only from environment to receiver communication, if is only by environment to receiver one-way communication, it is always possible to discriminate two orthogonal bipartite states. And
Pratik, can I
Yes.
ask a question? Probably I've missed something. So when you're upon the action of the channel on the psi state, is it
Yes.
necessary that the two states that will come out, they will always be orthogonal?
Yes, because you see, I have already said that in
It's an
the
isometry.
isometry. Yeah.
Yeah. Okay. Yeah, thanks.
Okay. So then from here, so by environment to receiver, one-way communication, they will be able to reveal actually which index was being made, encoded in the state, and they will have a LOCC2 information between sender to receiver. So for any qubit channel, you can show that this is the case. And even if you take the qubit channel to be completely depolarizing channel, means all the states, so even if the state is like this, the channel is like this, the whole block sphere, after the channel action gets mapped to identity by 2, then also you will have full information after the environment correction. And that is trivial because if you, so either your initial state, your initial state was pure and orthogonal. Now, if after the channel action, if the receiver end is I by 2, then the receiver environment state is a maximally entangled state. And this is maximally entangled state, and maximally entangled state also are distinguishable by one-way LOCC if there are two of them. So even for this kind of channel where there is no information at the receiver end, all the information is in the correlation. So this is important. This is because neither the environment has the information, individually environment has zero information, individually receiver has zero information, and all the information is encoded in the correlation of the maximally entangled state. And now by using LOCC, local operation and one-way classical communication, you are able to retrieve the whole information back to the receiver. So that is why this is a very striking as well as very interesting result. And as a corollary, you can have this thing that for any channel, lambda, which acts from CD to CD, the corrected capacity is always lower bounded by log2, because for any channel you can always find two states and two orthogonal pure state and encode it such that this Hardy-Walgett result is applicable, and you can at least have log2 amount of information being conveyed from system to referee with environmental assistance. So for any channel, the corrected lambda is corrected capacity is always lower bounded by log2. So today I'm stopping here, and tomorrow I think I will discuss two more results regarding this classical capacity, and then I will go to the quantum capacity, environment assisted quantum capacity of a channel, and I'll talk a little bit about the connection about this environment assisted capacity and Birkhoff's theorem.
Hello.
Yes.
So from mathematical point of view, the action of the cooperation between environment and the receiver is nice, but from the practical point of view, so where there is no cooperation between environment and the receiver. So in that scenario, how these LOCC things can be realized, like from the practical point of view?
No, I mean, if you don't have any cooperation from the environment, then there is no question of environment assistance capacity. You are only left with normal capacity, classical capacity.
So in this environment assisted capacity, so is it practically realizable, like from
Practically, yeah, I mean,
practical point of view?
yeah, I mean, you can think of a scenario like this, like let's say, uh, you can think like this, that okay, I have a system, so this is my system, and this is my environment, a big environment. And after the system environment interaction, my information from the system has been leaked into environment, but this information has not spread through the whole part of the environment. It is actually localized up to some domain of the environment. And it may be the case that this domain where this information has been spread, that portion you have access to. Maybe you don't, for this, you don't require the access to the whole environment. But to some local degree of freedom, you have the access that you can make measurement on the environment and take the classical information and you use it to correct your channel, correct your state of the system part, and then it is physically possible. But if you are saying that, okay, if some information is, when it is leaked, it is actually scrambled to the whole environment, and if I don't have any access to the whole environment as a whole, then I think this is not the optimally, I mean, you cannot answer this question of environment assistance, but also you can ask a question like, okay, if I have limited access to the environment, how much amount of information can I retrieve more? May not be the case that you are optimally retrieving the whole information, but at least it is an improvement over only looking into the system.
Oh yeah, thanks.
I think
Hello, Pratik. Yeah. Yeah. Can I make a slight comment? I think, as you said, for this completely depolarizing channel, I think it is not necessary that the means receiver and the environment should be in the maximally entangled state. Means you can think that the environment is actually I/2, and you are applying basically again a swap operation between the system and environment. So the environment comes to the receiver end. But what happens, actually the sender message now directly come to the receiver's, to the environment's hand, right?
Yes. Yes,
So,
if you, I mean,
I can
yes.
also think like that. Obviously, this MES is a simple structure. Even if you say that, well, I have the biggest environment, then finally it is somewhere maximally entangled state.
Yes.
But in principle, it is not true always that all the information is actually hidden in the coding. It may happen that the information is also in the environment's hand also.
Yes.
Right.
Yes. It is possible because so my argument was from this isometry picture. But as you are saying that if you take the unitary picture and this environment, it is very much. Yes.
Right. And another thing, I think this Kunika was also asking about that. I was also thinking, you see, it's really interesting that for getting the environment assisted capacity, you actually, if you want to get some assistance from the environment, you have to encode your message in the orthogonal quantum states, right?
Yes.
But the interesting thing is that in classical communication scenario, we have some instances where for optimizing the classical capacity, we need non-orthogonal states.
Yes. So if you are actually using this non-unital channel, then without the assistance of environment, it is better to encode the
non-orthogonal state. If you do not have the access to the environment, then there could be some scenario that where the non-orthogonal encoding is possibly the best encoding.
Yes.
Actually, there are examples.
Yes.
But as apparently it looks like that if you want to get access from the environment, then the orthogonal encoding is best, even for this kind of channel also.
Yes, because actually you are evolving with, you have the unitary freedom.
Right.
So,
yeah, so this is actually very interesting. When Kunika was asked, I just was thinking about it. Yes.
Yeah.
Yeah, thank you. Nice talk.
Thank you.
Yeah, nice talk indeed, Pratik. So maybe if there are any more questions, please ask him by email or maybe in the next week. Thanks. Next week you will continue the later part, right?
Yes, yes, yes.
Oh, okay. Okay. Bye, everyone. Thanks, Pratik.
Thank you.